Have you ever been totally stumped by a Sudoku? You plug it into an online solver and bam, the answer appears instantly? It feels like actual magic. But what you're really seeing is one of the coolest and most elegant strategies in all of computer science. So how in the world does it work? Let's get into it.
When we look at a puzzle like this, we see a real challenge, something that's going to take some serious thought. But a computer? It just sees a system of rules that it can solve methodically. So, what is that method? How does it nail a perfect solution every single time without fail?
Okay, so first things first. Before a computer can even think about solving the puzzle, it has to understand the rules of the game, just like you or me.
And the rules are super simple, but they are everything. A number from 1 to 9 can only show up once in any given row, once in any column, and once in any 3x3 box. That's it. Those are the 3 commandments, and every single decision the computer makes gets checked against them. This is where things get really interesting, because the computer's approach is totally different from ours. It doesn't have hunches or intuition. It uses a methodical, yet surprisingly clever kind of logic. So what's the computer's big secret? It's not afraid to be wrong. The entire strategy is just built on trying out possibilities in a super-structured order until one of them works. It doesn't guess, it tests systematically. And that relentless, patient approach, well, that's its superpower. This whole strategy has a name, and it's called backtracking. Honestly, the best way to think about it is like you're trying to solve a maze. You pick a path, and you follow it until you hit a dead end. Do you just give up? Of course not. You go back. You backtrack to the last place you made a choice, and you try a different path. That is exactly what the computer does with numbers. So here's the game plan, and it's so simple, it's brilliant. The computer finds the very first empty cell and just tries putting a 1 in there. It asks, is this legal? If it is, great. It moves on to the next empty spot. If not, it tries a 2, then a 3, all the way to 9. But here's the kicker. What happens if it tries all 9 numbers and none of them work? Well, that's when the real magic of step 6 kicks in. All right, enough talk. Let's actually watch this plan in action. We're going to follow the algorithm as it makes its very first moves on our puzzle here. Okay, here we go. The process starts. The computer scans the board and finds that first empty spot. Its first move is always predictable. Try the smallest number. So it tentatively plops a 1 in there and runs a quick check. Does this break any of our 3 rules? And it's a yes. The 1 is a totally valid move. So it places the number and immediately moves on to the next empty cell. This is where a cool process called recursion kicks in, which is just a fancy way of saying the program basically calls on itself to solve the rest of the puzzle from this new starting point. It's building the solution piece by tiny piece. Now, a straight line to the solution would just be too easy, right? The real genius here is what happens when the computer makes a mistake and literally walks itself into a dead end. So a few moves down the line, the solver hits a wall. It finds an empty cell. Tries a 1? Nope. Tries a 2? That's invalid too. It zips through every single number all the way up to 9 and realizes that because of the choices it made earlier, nothing can legally go in this spot. The path it was on? It's a failure. And this is the magic moment. The program doesn't panic. It just calmly realizes, well, my last move must have been wrong, so it goes back to the previous cell, erases the number it put there, and simply tries the next option on its list. It's undoing its own mistake to find the right path forward. This slide shows that critical fork in the road perfectly. Path A, where it tried putting a 1 in that earlier spot, led to this dead end. So the program backtracks, erases it, and moves on to path B, trying the next possible number. Maybe it's a 4. And this time, hey, the move works. A whole new path forward opens up, and the process just keeps on chugging from there. This cycle, place, check, and backtrack if you mess up, is the engine driving the whole thing. It's this relentless process of moving forward when you can and taking one step back whenever you hit a wall. This is happening thousands of times a second, exploring this huge tree of possibilities to find the one single path that solves the entire puzzle.
So, this process just runs and runs until the board is completely full. But the implications of this simple technique go way, way beyond solving a puzzle.
The goal is really simple. Find one valid solution. Not all of them, just one. The second it places that final valid number in the last empty cell, its job is done. Mission accomplished. And just like that, it's done. After countless tiny decisions of trial, error, and backtracking, every single cell is filled. The computer has navigated the maze and found the one true path to the end. The puzzle is solved.
So why is this so important? Because this exact same logic, explore a path and backtrack from dead ends, it powers so much of our world. It's how your GPS finds a route when the main road is blocked. It's the logic behind the AI in games like chess. It even helps giant logistics companies figure out the absolute most efficient way to schedule their deliveries. So next time you see a computer solve something impossibly fast, remember the simple, patient logic of backtracking. It's a powerful reminder. Even the most massive problems can often be solved by just methodically exploring every path, and most importantly, knowing when it's smart to turn back and try again. Which really makes you wonder, what other impossible problems could we solve just by thinking this way?